Hey guys, Mr. Middleton here. Today we're going to talk about solving systems of equations by substitution. At the end of this video, you should be able to solve a system of equations using the substitution method. Alright, so remember that we've already talked about solving systems of equations by graphing. Okay, but we'll actually want to know some different methods in order to solve systems a little bit more efficiently. Okay, and we'll change, we need to know differently because there are some drawbacks to graphing, to solving systems just by graphing. Okay, first drawback is the intersection of the lines may not always be on the graph. Okay, we talked about this just a little bit yesterday, but if we're given a graph, okay, there are some times where we know our solutions, our system's not going to have a solution because the lines aren't going to touch because they're parallel. But let's say, for instance, that we have a graph like this, given two lines. Are these two lines parallel? No. Do we know where they intersect? The answer is no, we don't. They will eventually intersect, we can tell because they're not parallel, but they're going to intersect off of our graph. Okay, and so the intersection is just not on the graph. Okay, and sometimes the intersection of the lines is not at a nice point. So even if we did see it, it's just not at a place that we can know exactly where it's at, if it's a fractional or decimal answer. Okay. Another thing is that we always had to put both lines in slope-intercept form, so it was a lot of work to get to it. And again, if our y-intercept is not a nice number, it's going to be hard for us to accurately graph it. Okay, so this next method, substitution, takes care of these issues. We'll be able to get an answer no matter how big or small the number is. We'll be able to use fractional answers, and we really don't care whether we don't have to put both equations in slope-intercept form to do it. Okay, so for substitution, our goal is to solve a system of equations by changing one variable into an equal expression containing the other variable. In other words, instead of using two variables, we'll only have one. Okay, so here's the big thing. It's important to get one variable by itself on at least one of the equations. Okay, so we'll kind of ramp it up, start from easy and kind of increase our difficulty from there. So in this first problem we have y equals x minus 7 and 2x plus y equals 8. Again, remember this is a system, these two go together. Okay, we're trying to find out the value for x and y that makes both of these equations true. Okay, in solving for substitution, what we'll try to do, our first step is to try to get a variable by itself. And we'll look at each of these equations independently. So here, y equals x minus 7. Here, 2x plus y equals 8. As I look at these equations, I'm going to say to myself, hey, in this first equation, I already have y by itself. Okay. Now, we call it substitution because now, in the second equation, well, let's talk about the sign equal and what the word equal means. Okay, equal means the same as. Let's say one of the things we can say equal means is the same as. Okay, have an equal amount of food, we have the same amount of food. Okay. So y equals x minus 7. Y is the same as x minus 7. Now that's important because we're going to substitute in our next equation. In this next equation, instead of writing y, we need to find a way that we can solve this equation and not have to write y. And this is where substitution comes into play. If I say that y is the same as x minus 7, in this equation, instead of saying 2x plus y equals 8, I can say 2x plus, and now like I just said, it's the same as x minus 7. equals 8. Okay, so I substituted x minus 7 for y. And I can do that because this first equation said that y is the same as x minus 7. Okay, and so now I can drop these parentheses and I have 2x plus x minus 7 equals 8, or 3x minus 7 equals 8. I'll add 7 to both sides, and I get that 3x is 15, and I can find that x is 5 from there. Okay, once I find that x is 5, I can plug this into the equation, either equation, and find out what y is. Probably be smarter for me to plug it into the top equation because y is by itself. So now I can say y equals 5 minus 7. Okay, 5 minus 7, negative 2. All right, now as we solve these systems, remember that we're really solving the same problem in a different way. So our solution should look the same. When we solve by graphing, our solution look like a coordinate. So when we solve by substitution, our solution will also be a coordinate. Okay, so my solution is 5, comma, negative 2. My x value is 5, my y value is negative 2. Okay, let's look at the second problem. In the second problem, we have x equals negative 2y plus 1, and x equals y minus 5. Okay. Now, notice that in this system that both equations have a variable by itself. Top equation has x by itself. The bottom equation has x by itself. Okay. We'll still solve this the same way. Okay. X is the same as negative 2y plus 1. So now in my other equation, instead of writing x, I can substitute negative 2y plus 1 in for x. So negative 2y plus 1 equals y minus 5. Now we have an equation with just one variable, so we should be able to solve it. I'll add 2y to both sides. I'll add 5 to both sides. And I find out that y is 2. Now that I know y is 2, I can plug this into either of the equations. I'm going to plug it into the second one. So now I get x equals 2 minus 5. So x equals negative 3. Again, my solution, my x is here at negative 3. My y is here at 2. And so there's my answer. Again, really nice here because we didn't have to change anything to slope-intercept form in order for it to work. We just had to have a variable by itself, which we started off with x by itself. Now, we're not always going to start off or get a problem where the variable is by itself. So, in the case that we don't get that, then what we have to do is get a variable by itself and choose what's going to be in the best position to do that. Let's look at that situation here. We have x plus 4y equals 11, and 3x minus 2y equals 19. Okay. As we look at these two equations, we should ask ourselves, is a variable by itself? In this case, the answer is no. Then we should say, which variable is going to be the easiest to get by itself? As we look at these two equations, you should notice that we have a bunch of variables, bunch of variables, bunch of variables. Okay, x's and y's in both equations. But this x is positive and by itself. So that's probably going to be the one that's going to be the easiest to get by itself. How do we get it by itself? Well, we have to move 4y. And we do that by subtracting 4y from both sides. And so I get x equals, let's just write negative 4y plus 11. Okay. And now I have the x value by itself. And now in my second equation, I'm going to substitute in for x. So now, since x is the same as negative 4y plus 11, I'm going to write 3 And now instead of using x, I'm going to say negative 4y plus 11 minus 2y equals 19. Okay, and now I have an equation with just one variable, and so I'm able to solve it. So I solve through negative 12y plus 33 minus 2y equals 19. I'll combine my terms here. Negative 14y, subtract 33 from both sides, and that gives me equals negative 14. And so y will be 1. And now that I know that y is 1, I can plug that into my equation with x by itself. And actually, it'll probably be, you can plug it into this equation by itself if you're really sure of it. But the best thing that you could do is plug it back into one of the original equations. Okay, and this way you get to kind of check your work. Okay, so either way, you can plug it back in here if you're really sure about it. I'm going to plug it back into this original equation and say x plus 4 times 1 equals 11. So x plus 4 equals 11. Subtract 4 from both sides, and x equals 7. Okay, we should be able to plug this back into both equations, and both equations should be true. So we have 7 plus 4 equals 11. We have 21 minus 2 equals 19. They both work out. 7, 1. You can do that check each time if you'd like. Okay, so if you want to know how do I check my answers, that's how you check your answers. You have an x value and a y value. You can plug them back into both equations. They should work for both equations. Okay. All right. I would like for you to try this last problem out and bring it to me completed. Okay. So look at the problem, say which variable is going to be the easiest to get by itself. Get it by itself, substitute it in, and solve for both x and y. Alright, flipping to the back. Let's look at some special cases. Alright, we had special cases with graphing, and because we're still solving the same type of problems, just using a different method, we'll still run into those same special situations, but they'll look differently. With graphing, we just knew they were special because either we had one line or because we had two parallel lines. If we're not graphing lines, we won't see them as that. So let's see how these special cases roll out. Alright, so here we have y by itself in the second equation. Y is already by itself, so what I'm going to do is instead of writing y in our first equation, I'm going to plug in negative 6x plus 1. So I have 6x plus negative 6x plus 1 equals 10. Alright, 6x plus negative 6x, so plus a negative means minus. 6x minus 6x gives me 0 x's. So 0x plus 1 equals 10. And I really don't need to write 0x, just writing that. Oops, can't see it anyway. I really don't need to write 0x, I'm just writing that because that's what we got. Okay, that really will cross out. And so what I get is 1 equals 10. Does 1 equal 10? No, it doesn't. Okay, and so what I have here is a no solution. It's a no solution problem. Okay, and just like when we were graphing, when we had no solution, we knew that our lines were parallel. Okay, again, this is just a different way to see the same type of problem that we did with graphing. Okay, our lines would be parallel here, there's no solution. Okay, let's look back at the top, or let's look at the second example. Okay, we have 2x plus 4y equals 8 and x equals negative 2y plus 4. Again, I have x by itself in the second equation, so x is the same as negative 2y plus 4. So I'm going to substitute this in to the first equation for x. So now instead of saying 2x, I'm going to say 2, negative 2y plus 4, plus 4y equals 8, because x is the same as negative 2y plus 4. I'll distribute negative 4y plus 8 plus 4y equals 8. Negative 4y and positive 4y, when I put those together, it gives me 0, y. So 8 equals 8. Is that true? Yes, 8 does equal 8. And so, there's no way I can mess this up. There's no value that doesn't work. So, I'm going to say there's infinitely many solutions. The lines would be the same or coinciding. Okay. These two examples are special cases, just like we talked about yesterday, yesterday with graphing. In both examples, the variables cancel out. So how can you tell the difference between no solution and infinitely many solutions? In no solution, the variables cancel out and the remaining numbers are not equal. The remaining statement is not true. Okay? Like we had it here where 1 equals 10. That was not a true statement. Okay? In infinitely many solutions, the variable cancels out and the remaining numbers are equal. The remaining statement is true. 8 equals 8. Okay? So, there's solving systems by substitution. You have that last problem to do. Remember to get that variable by itself, plug it in, substitute it to the next equation, solve for your first variable. Once you get that value, plug it back into the second equation, solve for the second one, and leave your answer as an ordered pair. Alright guys, see ya.